necessary for this class. All right, so let's investigate Jeff Leake's website, because Jeff Leake's website is blowing up. So consider the daily counts to his website. Here's his website. You can all go to it and increase his number of hits. So in every instance, the unit of time is always 1 day. So we're just setting t equal to 1, right? As 1 day. So the Poisson mean is interpreted as web hits per day. You know, if we'd set just to give you how this works, right? If we'd set t equal to 24, then and the measurements were in the per day, right? Then the lambda that we would get out of the model would be interpreted as web hits per hour. And okay, so it's that. I hope everyone sees that. That's easy. And we'll go through an example later on of how you actually incorporate, let's say, one. And it's very easy if everything was measured for the same amount of time. But let's imagine if one count was measured in a day, and then the next one was measured in a half of a day, and the next one was measured in a day, and the next one was measured in a half a day, or something like that. I don't know why that would happen, but let's say someone, for I don't know, whatever, there was a mess up in the program, and every other day it only recorded half a day's web traffic. We'll show you later on in the lecture how to have a varying t value for every observation in your regression model, your Poisson regression model. So here it is. You can get it. I think Jeff put it on Dropbox. The Julian dates are these. They're a count and a number of days from a specific date. The nice thing about R is when it prints it out, though, it prints it out in a nice formatting, as we can see. And so here's the outcomes. It looks like he's not getting very many visits. He's not getting very many visits on these days, but you can see, let's just double check, right? We can see that the measurement is every day, and then here's the exact. I'm sorry. Here's the Julian dates. I guess I'm wrong. R doesn't automatically print the Julian dates out as dates. So here's the original date variable in the date-time format, and here's it converted to Julian dates. So you can see that they just increase by 1 each time, right? So because Julian dates are a measure of the date from a specific date in days. Okay. So here's a plot. Looks like, you know, looks like Jeff is blowing up. So we could model this as linear regression. So, and we've talked a lot about linear regression, so let's just go through how we would do that just as a refresher at this point. And because you guys are all linear regression ninjas at this point, this would be no problem for you whatsoever. So you could model the number of web hits as having an intercept and a slope times the day, and then you could add an error term, right? Just a standard linear regression. You know the interpretation for all this at this point. Oh, and Jeff gives the Julian day 0 there. Let's see. So here's the plot of the fit, and that looks good. And we'll talk in a minute about why you might want to model this instead as Poisson. But before I do that, I want to talk about an aside. Maybe one of the reasons you might want to model it as Poisson is because you want to talk about relative increases or decreases in web traffic, right? You want the coefficients to have relative meaning rather than absolute change meaning. And that would be that's nice, right? That's something something seems pretty reasonable about doing that. And I just wanted to mention that one idea you might think of is to just take the natural log of the outcomes. So that would just be exactly this model, that the log of the web hits is a line. And this is not the Poisson model, right? The Poisson model is going to model we talked about GLMs, it's going to log the mean of the y's, the conceptual mean of the y's, not the observed mean. So that actually avoids some trouble. So logging the outcomes has a problem, as we saw that the first couple of days the number of web hits was 0, and so you can't take log of 0. So that's a problem. But it also has a very different interpretation. So if you just log your outcome and you're happy with interpreting on the log scale, then so n number of web hits is still the number of web hits. Julian date is the Julian day. B0 is the log number of hits on day 0. B1 is the increase in the log number of hits per unit day, and E is the variation. Epsilon is the variation, or Jeff wrote it as E here. But what's interesting about logging outcomes is it's a very special transformation in that it imparts kind of a particular interpretation of the coefficients when you exponentiate them. So I'm going to define this guy, and maybe it's a little small, so let me just write it out bigger. E to the expected value of log y, where y is any random variable, it has to be positive. Kind of only makes sense to do this for positive random variables. Is the so-called geometric mean of y. And you might have heard of the geometric mean and say that does not look like what I've heard of. But I'm thinking of this as the sort of population geometric mean. If you just had a bunch of data, if you just have y1 to yn, and you wanted to estimate that, then you would just estimate this expected value with the average. Let me write it out a little bit bigger. So we would clearly just e to the 1 over n summation I equals 1 to n log yi. Clearly, if we wanted to estimate that guy, we would just plug in that for that expected value that we don't know. It turns out that this is equal to just the product I equal 1 to n yi raised to the 1 over n power. And at any rate, the geometric mean is this is what probably most people have heard of as the geometric mean. But that's an estimator, and what's its estimand? Well, that guy is its estimand, right? That's what it's estimating. If you collect an infinite amount of data, it converges to that. The geometric mean is the natural model for anytime you want to model something that's a relative quantity. So if your data is a bunch of percent increases or decreases, then clearly the natural definition of the average is some sort of multiplicative average, not some sort of arithmetic average, the standard average. And because when we think of these percent increases or decreases, we multiply them, right? If you have your data point is 1.03, representing a 3% increase in whatever, then that number intrinsically has a multiplicative interpretation. And so the geometric mean is extremely useful for that. So anyway, here's my point. When you take the natural log of outcomes and fit a regression model, your exponentiated coefficients estimate things about geometric means rather than about the natural scale means. Okay? So in this case, in our exact example, e to the beta naught is the estimated geometric mean hits on day 0, and e to the beta 1 is the estimated relative increase or decrease in the geometric mean hits per day. And if we had other covariates, we would have to add the phrase holding all the other covariates constant. There's a problem with logging the outcome if you have 0 counts, and in fact, this is a problem in this particular data set. The thing that people often do is they just add a little constant. So instead of modeling visits, it's visit plus 1 or plus 0.5 or something like that. The problem with that, of course, is that the interpretation is no longer it's not the estimated relative increase or decrease in geometric mean hits per day, it's the estimated relative increase or decrease in geometric mean hits plus 1 per day. And so it messes up the interpretation a little bit, but for the time being, let's forget about that and just interpret this as if we didn't add the plus 1. Okay? So when we do this model with the logged outcomes, and I'm printing out the exponentiated coefficients to 5 decimal places, and so we get 0.002, 1.002. So that's representing a 0.2% increase in web hits per day. Okay? And that's nice, right? Because it's a relative interpretation, which is kind of what we want. We want to talk about our web hits increasing in as percents rather than talking about the raw number of web hits we get per day. And it's especially useful, if your traffic is really exploding, right? And it's more meaningful to talk on the log scale than on the natural scale. Okay, so that's logging. Logging in the mathematical sense, not like with an axe. Okay, let's compare linear and Poisson regression, and I'll also add some thoughts about logging versus logging the outcomes versus a model with a log mean. Okay, so linear just models this guy, that the number of hits is has a linear relationship, and that implies an expected value relationship between the outcome and the linear predictor. The Poisson log linear model models the log of the expected value as the linear predictor. Okay, let me do that again right here. Okay, or you can invert that statement and get that the expected value is the exponent of the right hand side. Okay, now notice from this equation how we might interpret beta 1, right? So we might say expected value of number of hits for a Julian date equals, let me just say j plus 1, so minus expected value of number of hits given the Julian date equals j, right? That works out to be b1, right? And so raising that e to the b1 then is the relative increase in the relative increase in the mean number of hits per 1 day increase. And then if we add other covariates, it would be the relative increase per day, holding the other covariates constant. I just want to add on the slide, it's not on the slide, but just because I added a little text on it earlier, then there's the other option of modeling the log counts, right? And how is that different from modeling that? And that is a model on expected value of the log of the number of hits, right? Which differs from what the Poisson model is accounting for, right? This guy, because expected value and log can't switch, this guy logging the outcome is a model on that, whereas this guy is a model of the log of the expected value. So the Poisson model, the coefficients are going to be naturally interpreted in terms of the expected values of the outcomes. The geometric mean is going to be kind of naturally interpreted the expected values on the log scale. So at any rate, that's the difference between logging your outcomes and fitting a model where the linear predictor is on the log of the mean. Okay. So just to reiterate, right? So the expected value of that is that guy, right? Expected value of the number of hits is that guy if we exponentiate both sides of our log linear model. And then we can, of course, pull out the E of beta naught, and then Jeff is just reiterating that if the Julian date is increased by 1 unit, then the expected value is multiplied by e to the beta 1. So e to the beta 1 is the relative increase or decrease in web hit, in expected web traffic per 1 day increase. Poisson regression in R